Yeah, hi. Good evening, everyone. Am I audible?
Yes, sir, you're audible. Good evening.
Okay. Thanks. Okay, so today is the second revision session for quiz 2, and we have the plan to discuss this week 7 and week 8 some questions. And if you have any doubt, that you can also ask. Okay, so let me share my screen. One second. Okay, I hope you have tried to solve that mock questions. If you have any doubt in the mock, then you can ask, clarify that doubt. And we have another some set of PYQs from the week 7 and 8 for today's session. And we will discuss how to approach to solve the questions, so all these questions. Okay, so I think these will be help to you for the exam also. Okay, so before starting, if you have any query, you can ask in starting. If you have any specific doubt. Okay, so I have this peer deck link. You
Sir, you
can.
are not audible.
Am I not audible? Is it for everyone? Hello.
You're audible, sir.
Someone said I'm not audible. Okay. Okay, Aman. Thanks. Yeah, please check your network. Who said? I'm not sure who said, but you can check your network. So I hope this screen is visible to all. So this is one peer deck slide link. So joinpd.com, and this is the code. Okay, so I'm sending this in the chat. This link I'm sending in the chat. You can directly open this. Okay.
Hello,
So
sir.
yeah, Laksh.
Hello.
Yes, Laksh.
Hello, sir.
Yes, Laksh. So you are audible to me. Am I audible to you? I think some issues from the Laksh side. So Laksh, you are not audible to us. I think so.
Yes, sir.
You can.
Hello. Am I audible now, sir?
You are audible.
Yes, sir. I have a request that when you solve the question, can you please summarize the concept which would be used in that question also, sir?
So that would be automatically covered. Okay, so what concept we are using to solve the problem, so that by default it will come. Okay.
Yes, sir. Yes, sir.
Okay, so I have shared the link of these some set of questions. So you can open from your side this also. So just you can also open this joinpd.com, and after that just put this code. Okay, this code I have also shared in the chat. After that you will get access for these slides. Okay, so let's start. So now from week 7, basically we have the topics like greedy algorithms, where we started from the AVL tree. Uh, okay, where to enter the code? So yeah, just join.pd. This is a website,
Sir,
join.pd.
sir, can you also just summarize concepts? Like some concepts are not discussed in the
Which,
lecture, like rotations. Sir has explained only RR and LL, like
okay.
LR and
Okay,
RLR.
so I think I have one question on the
Curves.
AVL. I have one question on the
Yeah,
AVL.
yeah.
So during that, I'll explain. Okay.
Okay.
Okay. Okay, fine. So let's start. So I'm starting from the week 7 question. So now we have some. So you know that in week 7 we have started with the binary search. Okay, but that binary search was balanced binary search. So balanced is required if you want to use their operation efficiently. Otherwise, binary search, the tree actually may be the skewed tree. So where we cannot take the advantage of the efficiency of the binary search operation. So because of that, if our binary search tree is balanced, then we can achieve our complexity log n for searching, insertion, and deletion operation on the binary search. Okay, So here we have one question based on the binary search tree. So I hope you know the properties of binary search. So where the uh, for every node in the left subtree, the value of the left subtree will be less than to the every node. Okay, and value of the right subtree nodes will be greater than to the current node. So if we are talking about like here A, if we are talking about A, so all the nodes which are coming on the left subtree, the value of all of these nodes will be lesser than this A. And all the nodes which are coming on the right subtree, the value of that node will be greater than to the node A. So this property is actually included for consider for every node in this tree. Okay, so same you can apply on the B. So you can see what are the nodes which are coming on the left subtree. The value should be less than to this B. Okay, and what are the nodes which are coming on the right subtree? This E, J, K, that should be greater than to the B. So this property implies by default for every node. So and then this tree is called binary search tree. So this is the property of binary search tree. I hope you should know how to create the binary search tree. So that is important one type of question. So if any sequence of elements are given, and if we ask that create a binary search tree, so that you should know how to create the binary search tree. Okay, some question maybe depend on this also. So let me just clarify that things, because that is very important for insertion and for searching. So suppose we have given some random sequence like 10, 2, 5, 6, 8, 20, 15. Okay. And this sequence is given, and we are the question is asking to create the binary search tree for given sequence. Okay. So how we can create? So we start the left to right, and we take one element at a time, and we insert that into a current binary search tree. So initial our binary search tree is empty. One second. So now we will insert that 10 node as a root. Okay, because this is a empty binary search tree, so this 10 will become a root. After that, when we will take the 2, so the process for inserting is always start comparison from the root node and then check where you are getting the empty place and then add that. Okay, so how we can compare? So just compare this 2 value with current root node. Okay, so we will always start from the root node. So 2 is smaller than this root node. So that means you should traverse to the left side. If value is greater than, traverse to the right side. If value is lesser than, traverse to the left side. If node is not there in the traversing, then insert that element at that place. Okay, so 2 is less than, so we will traverse to the left side, but there's nothing on the left side connected to this. Okay, so we will just insert this at left. Okay, now 5 again we will start from 10. So 5 is smaller than 10. We will move to left. Okay, left is there, left child is there here. Now we will do the comparison again. So 5 is now greater than 2. So this means we should traverse to the right of this 2. So but there is no node connected to this. So we will add this 5 on the right of 2. Now 6, again we will start from 10. 6 is less than 10, move to left. Again compare with say 2. 6 is greater than 2, move to right, but right is also there. Now 6 is less than 5, so move to left. And if this is the empty place, add this. Okay, now 8 is again less than 10, greater than 2, less than greater than 5. So this is the empty place.
Sir, six is greater than 5, no?
Sir, 6 should come on the
Correct. So 6 is greater than 5. Correct. Now 8 again less than 10, greater than 2, greater than 5, greater than 6. Yeah. Okay, 20 is greater than 10. So just yeah. 15 is greater than 10 but less than 20. So this 15 is connected here. So this is the way to insert a node in the binary search tree or create a binary search tree for the given sequence. Okay, this should be very clear. Okay, because the same method we used for the creation of AVL tree also. Okay, because of that, this is required to know. So now this is the things. So you can see this is not looking like a balance. Okay, so here you can see this is the very long path, and this is very short path on the right side. So this we cannot say that this is a balance, and we need a balanced binary search tree. So that then we use the AVL tree. Okay, for that question, let's see for this question. So consider the following binary search tree. The letters indicate the name of that nodes, not the values that are stored. Okay, letters indicate the names of the node. Okay, what is the predecessor node in terms of value of the node M? Okay, so here actually this is a binary search tree. Okay, so because of that, all the nodes are containing in the all the nodes are actually in proper order. Okay, in the binary search tree, but these are just a name, A, B, C, D. These are just a name of node, not the value. So now we are asking that in the terms of value, what is the predecessor node of M? So predecessor means if we arrange all these nodes in the sorted order, then suppose we are getting the order. One second. So suppose we are getting the order like 10, 20, 30, 35, 40, 60, like this. So suppose we are asking the predecessor. Predecessor is just a previous element in the terms of value. So suppose we are asking the predecessor of 40. So predecessor of 40 is 35. Okay. And successor of 40 is this 60. So in the sorted sequence, which node is coming just before? That is called predecessor, and which node is coming just after that? That is successor. So the question is asking like this. So which node is the predecessor of value M? This one second. I have to use the pen.
So whenever there is nothing mentioned like predecessor, so we will take it as in order predecessor.
So here it is mentioned, na? So in the terms of value. Okay, in the terms
But
of
the
value.
question asks only the predecessor. It doesn't say pre-order predecessor or post-order predecessor or in order. We'll take in
No,
order.
no, no, no. So here there's nothing related to the in order or predecessor like these things. Predecessor means in the terms of value. So which one is the just nearest value in the smallest side of that node. So here in order, post order, this is doesn't matter. Okay, here our task is just figure out the value. Suppose M is 40. So what value is the closest on the smaller side of this? So that value we are figuring out. But to solve
So,
this, we use the in-order traversal because in-order traversal provide a sorted sequence.
sir, predecessor in the list, not in the tree. So we have to get the
Here,
list
this is a binary search tree, not just a tree. Okay, this is a binary search tree where data is arranged in order. Okay, here data is arranged in some systematic way according to the binary search property. So because of that, we can take the advantage of binary search tree in searching, insertion, and deletion, this type of operation. Because data is, we know that how we can search the data. Okay, because all the small elements are coming in the left, or all the smaller elements are greater elements are coming on the right. So this property we can apply at the time of searching, at the time of insertion, at the time of deletion. So because of that, this arrangement is called as a ordered collection. Okay, ordered data.
So why can't we simply say G is the predecessor in terms of value?
No, how this is possible?
G
M will
could be
be smaller
successful.
than G.
What you said, G is smaller than M.
No, M will be smaller than G.
So then predecessor, how this M will become a predecessor? G will become a predecessor. Predecessor means just smaller value, closest smaller value of M. But here G is greater, na?
Yes, okay.
Okay.
So G could be a successor.
This could be successor, yes. Successor, it's possible. Okay. So now predecessor in the terms of value. So means we what things actually we required here? We required a sorted order. We need to figure out that how we can arrange these nodes in the sorted order. So here
Sir,
you can
a basic question. If in terms of value was not given, then the predecessor would have been G, is it?
no, then this question not make sense.
Okay, G is the parent of M and N. So
Parents. But how we can figure out that this is a predecessor? Because again, then I think then some order will be specified. I think that post order, pre order, in order, any traversal order will be specified. Then you can figure out this which one is the predecessor.
okay, okay, sir.
Okay, in the terms of node, without specifying the traversal order, then you cannot identify that which one is the predecessor and which one is the successor. Okay?
Okay.
But in the terms of value, you can easily figure out. So to identify the predecessor and successor, your task is just arrange all these nodes in the sorted order, in increasing order. Okay, so that we can do with the help of in-order traversal. Okay, so if you apply the in-order traversal on this tree on the root node, you will get a sorted order. So this is the by default properties of in-order traversal. If you apply that on the binary search tree, you will get a sorted order in increasing order. Okay, so then you can think you can apply this in-order traversal. So suppose you know that the what three steps are required for the in-order traversal. So first call is the left recursive call. Second step is just to print the current node. Okay, if we want to print the order, so I am just writing P. Okay, print that current node, and next is just move to the right node. Okay, so this is just a recursive call L. I am just writing as a L means left recursive call on the left child. This is also a recursive call on the right child, but this step is just to print the current node. Okay, so these three steps we can apply recursively, and we can get the in-order traversal. So if you apply this here LPR, so you can see the first step will be this. Okay, so this means apply the same recursive call on the left child. So just move here. So LPR. So left recursive call, again the first step of this call. So again move to left child. So this LPR, and this is again okay left. Now LPR. Here there is actually we are reaching at the base case, so means there is no left child here. Okay, so this step will not affect anything, so we will move to the second step of this call. So this is the print current node. Okay, so print current node is H, so this H will be print here, and then write recursive call. So write is also not there. Okay, so all three steps are complete, so means we will reverse back to the previous where we are coming from. So now first step is complete. Second step is print current node. Okay, so this is a D. D will be print. Then write recursive call. Okay, so write recursive call is a call. So write is available. So this means we will move to the right child. Sorry, PR. Okay. Now first step is left.
Sir, how you printed D, sir?
So this first step is complete. The left recursive call. So all the steps are completed of this left recursive. So we will come back to that step. Now this step is completed. So we will move to the second step, print current node.
I see. So print we have already used for H, no, sir?
No, that is a different call actually. Okay, so this is a recursive call. So means we are applying the same function on the left child.
Yes.
So all three steps will be applied on that node. Okay. So
thank you,
print, now write recursive call, we will move to the right child and we will apply the same function. So that first step is left recursive call, left is there. So here three steps we will apply here. Now node left child is here. So this step is done without any effect. So now print current node. So this is O. Okay. Now no right, all three steps complete, reverse back on the left. Now print current node. Okay, so I. And write recursive call. So move to this side. So L, P, R. No left, print current node. So P. And no right. Okay, all three steps complete. Move back. Now all three steps complete of this. Now move back here. So here all three completed. Now move back on the B. Okay, so now this left part is complete. So B, second step is print current node. So B. Okay, now right call. Okay, so this is a right call. And here LPR. So left recursive call again. So here come LPR. So no left, print current node J. No right. Okay. All completed. Now print current node E. And R. Okay. So just move LPR. No left. Okay. Print K and no right. So all done. Move back, right done, move back, right done, and move back. Okay. So now print current node A. And then move right. So here and left call and left call again. So this. So no left, print current node. So L right, no right. Okay. So now print current node F and no right. Okay, complete. Back, print current node C. Okay, and come back here. Okay, so P. So this move here L P R. Okay, no left, print M and no right. Okay, here you can see what was the question, predecessor of node M. So this is a increasing order actually in the binary search tree. All the nodes are coming in the increasing order. So what is the predecessor of M here? Just previous node C. So this is the answer in the terms of value. So this C node is actually a predecessor of this M in the terms of value. So in this way, you can just get the order. That order is represent the sorted order in increasing order, and you can figure out that which value is coming after which value, or which value will coming before the value. So in this way, you can solve this. So this is the in-order traversal algorithm. So I hope we have discussed this pre-order and post-order also in the weekly session. So similarly, only the steps are changed. Otherwise, the way is you can directly get the order. Like just this P position is actually changed. In the pre-order traversal, just P put this P print current node as a first step, then left recursive, right recursive, and post-order traversal L R P. Just push this P step print step at the last. So this is the only change in the traversal order. So answer for this question is C. Okay, C is the predecessor. And what is the successor of this? So just continue this. So that M we have printed, now G. Okay, so G will be print. G. And then N. Okay, so G is the successor of this M. So in this way, you can identify any predecessor. What is the predecessor of J? So that is B. What is the successor of J? E. So you can figure out this. I hope this is clear. Any doubt in this? Anyone?
No, sir. Sir, this in-order traversal is used to get predecessor in terms of value. Like this, are there
In-order traversal basically provide a sorted sequence of
Yes.
the elements of binary search tree.
Yeah.
Then we can figure out the predecessor and successor in the terms of value.
So are there any use cases for post-order and pre-order as well?
Post order basically used for some expression. Suppose if you have any arithmetic operation, so that have some different use case. So sometimes actually we also use that arithmetical that expression we have, suppose, and we create the tree for that. Okay, then we can generate the prefix postfix sequence for that, and after that expression can be evaluated with the help of postfix expression. So some use case are there of these type of traversing on the tree. If your tree contains the arithmetic expression information, suppose I'm giving the example here. One second, I'm deleting this. So suppose you have the tree like this. So plus 6 and 2. So generally arithmetic expression may be represented like this. Okay, so and we have suppose this type of expression 2 6 plus 2 and into 3 minus 1. Okay, suppose this expression is there. So how we can represent the tree for this? So tree can be represented like this. So this is done. Second part we will write 3 minus and 1. So this is like a operator, and this is the multiplication. 1. Okay, so in this way arithmetic expression can be represented. Okay, and after that we can how can computer can solve this expression? So computer, I think this is discussed little bit in week 3. Some question is there related to this, where the postfix expression is given. Okay, so postfix expression where the operands that operator comes before the operand. So this is called as a operand. Okay, so all the leaf nodes actually called as a operand. Operands means the data or variable. and the intermediate node is considered as a operator. So expression, if we find out the post order traversal for this, okay, so that suppose LPR, this, not this, sorry, LRP, okay, so this is the traversal. So just left call, just LRP, and again left LRP. So left, now this is done, no right P, okay, so 6 we are getting, and move back. So right is there, so move to this LRP, no left no right P, so 2, okay, so then this done P plus, okay, and now we move here, so right is there, so move to right, so LRP
6
left.
plus 2, right?
No, so this is post order traversal for this, okay, so this expression comes like this.
The expression which you wrote for that in order would be most convenient.
No. So for solution, actually, this expression can be solved with the help of stack. I'll show you how this can be solved with the help of stack. Okay. So here, first thing, we are getting the post order traversal, that is represent postfix expression. So 3, you can see, okay, so we have moved here 3, now 3 will come, and then this right will come 1, and then minus, okay, and then this will come multiply. So this is actually post order traversal for this tree, okay.
Yes.
Now how we can solve this with the help of stack? This expression generally solved by the computer using the stack. So now we traverse all the element if the current uh, operator or operand, anything, if this, that is operand, so we will push into the stack. If our current symbol is operator, then we remove 2 previous operand from the stack and perform that operation, and again push that into the stack. So that is, you can 6, okay, first this is 6, this is a operand, so just push into the stack 6, okay, I'm just representing the stack like this, okay. Now this is again 2, okay, 2. Now this plus is coming when operator is coming, so remove pop 2 previous, okay, top 2 elements from the stacks and perform that operation between them, okay. So 2 plus 6, so here we will just take like a, so this 2 will come as a second value, 6 will come here, and plus. So what is the current value? 8, okay. So we will remove these 2 and 6, and after that, after solution of this, we will post that result, so result will be 8, okay. Now next value is 3, next value is 1, so 1, now minus is coming, okay. When minus is coming, so we will remove 2 elements, so 3 minus 1 we will perform, and 3 minus 1 is 2, and 2 we will push again, so stack will contain now 8 and 2. Now multiplication is there, so again we will remove 2, 8 multiply with 2, and then 16, and 16 will be again push 16. So in this way, actually computer solves the expressions, okay, where the arithmetic expression represented by the with the help of postfix expression, and that order we can get with the help of post order traversal. So these are one use case, so you can explore more regarding this, okay. I hope this is clear.
Sir, are there some questions like this in late code?
No, this is the additional things, but yeah, programming question 1 assignment we have given in the week 3. I think GRP2 week 3
Yeah,
is
that
there.
is performed using stack.
So that is directly postfix expression is given, and you can solve that with the help of stack. But related to here, this expression tree, we are not generally giving. Okay, so for this, I've just mentioned the use case here, so where we can use the post order traversal or like this. So I hope this question 1 is clear. Any doubt in this, or shall we move?
Yes, sir. Let's move forward.
Okay. So next, this is the, again, I think, okay, so we have discussed this things lot here. So here some tree is given and some code is given, okay. So traversal is given, so you have to figure out that which type of traversal this is, okay. So can anyone tell me which type of traversal this is?
Post order.
So here traversal to the left, then traversal to the right, and then print, okay. So what order will be print? Okay, so this type of question may also be asked where the option will be given. In this slide, options I have not mentioned, so you can figure out that what order should come. So we have already solved the one post order traversal on the tree. So quickly we can solve this with the help of same. So L. So you can
Sir,
see, huh?
we did for in order, no?
No, this is post order. Here this code is given. Question is
This is
which of
post
the
order.
following order will be printed by the given code snips. Here I have removed the option. So okay, without option, without looking the option, you can just apply this code. Basically, this code is just representing a post order traversal. Okay, so that first step is left recursive call, second is right recursive call, and third step is print current node. Okay, just apply this. So left recursive call, move left, RP. Okay, again left L R P. Okay, now this complete P. Okay, so D will be print as first. And this step done, now move to right, so that LRP, now left call, so LRP, okay, left, no right, print current node, so H, and no right, print current node, E, okay, now right done, print current node, B, now left part is done, move to right, okay, so move to right, LRP, and left is there, move to left, LRP, left is there, LRP. No left, no right, print current I. Now no right, print current node F. Okay, right is there. So yeah, LRP. No left, no right, current P. So G step. Okay, now right is done, P, C. Okay, and P, A. So this order we are getting if we are applying this code is given. So don't require to apply this code. Okay, so just figure out that what type of this code is actually, which traversal it is representing, and you can just note down these three steps. Maybe sometimes suppose what happen if the first call is right recursive call. Okay, so just carefully see this code. What is the first recursive call? Suppose first recursive call is right t dot right. Okay, and then second call is t dot left. So these steps will become R, L, and P. Okay, this is not representing any specific traversal, but this is just a different version of traversal where we are moving right first and then left. So this you will get a just a reverse order of this post order like this. Okay, so you can directly apply this type of shortcut to solve this. So instead of to applying the code, okay, just a dry run on the code. So this is the order we are getting. So similarly, if any type of order is asked, you can apply. Okay, okay, this is clear, or any query in this?
No, so the answer will be post order.
So post order traversal, which I have mentioned in the screen, DHEBIFGCA. Okay, so this yeah, so more question about the AVL tree. You should know what is the different you know the balance factor.
Yes, sir. It
Balance,
should be between -1 and 1.
It is just the slope.
balance factor is just like absolute value of left height. Okay, so left height minus right height, like this. We can consider this, and this should be less than equal to 1. So this is the balance factor for binary AVL tree. Okay, if we are creating a binary search tree, so every time we calculate the balance factor for each node, and if that balance factor is less than or equal to 1 for every node, so we will consider that our tree is balanced. If at any point this balance factor become more than 1, then we applied the rotation to make balance. So this is the AVL actually rule, and some type of rotations are there. So we will discuss that if that next question, I think.
So,
Hmm.
so is it just the absolute of the slope?
So we generally take absolute. You can so in implementation you can consider anything. So you have to just apply some more condition then. If you are considering, so if you're not calculating absolute, it means, so this balance factor means this value. So this is just like an adjustment. So balance factor, if you're not calculating the absolute value, so this should be less than to my, this is balance factor less than equal to 1, and this side also, so greater than, sorry, greater than equal to, greater than -1. Yeah. So like this type of condition you have to validate. Okay, so their balance factor should be come in this range, -1 or 0 or +1. That is the possible case.
But sir, in the like previously you had just taken absolute, no, you had defined
So
like
that I am saying this is just like a adjustment. So we are say if we are calculating, so what was the formula we are taking actually? So we are taking the formula absolute of left height minus right height. So left subtree height minus right subtree height. Okay, this is the absolute formula we are calculating. So this is you will get always this positive because this is the absolute value. But if you are not taking absolute, so this thing you maybe get as a -2, -1, or 0 or 1 or 2 like this. All possible value you will get because maybe sometimes left height is greater, sometimes right height is greater. So based on that you will get this type of values. In that case, for the rotations like when you will apply the rotations, so at that time you will consider these three value as a balanced. Okay, so if you are getting these three value as a balance factor on the each node, so means that is balanced. One second.
sir, then it is not a directly balanced factor, no, it's the absolute of it.
No, that is fine. But okay, so
But yes, there is some confusion in that notation.
no, nothing notation. So I'm
So
just
previously you have written, no, like BF is equal to absolute of left
as I
height minus.
mentioned, this is just like a some adjustment. You have to just modify a little bit implementation. Otherwise, your task is doing the same. So what is the mean here? So suppose if this is the tree, okay, like okay. So now we are calculating the balance factor for this current node, the root node. So what is the balance factor value for this? So here, what is the left subtree height? If you are considering the number of edge in the longest path of the left subtree, then you can also take this as a left subtree height. Or sometimes you maybe count the number of nodes in the longest path, so that you can also consider. This side, suppose this you are considering number of edge. So this side number of edge are 2. Okay, so left height just you are considering as a 2 height. This side is 1 edge there in the longest path. So 2 minus 1 you are getting 1. So for the AVL definition, this one, if you are getting height difference 1, 0, or -1, so these height difference considered as a balanced. There's no problem with this. If you are not calculating the absolute difference, if you are calculating the absolute difference, so always you will get either 0, 0, or 1, or more than 1. Okay. In that case, you will only consider these are the balanced. Okay, because for the negative value this will also become a 1 in the absolute difference, correct? So means we are working on the same side. Like suppose if you are getting -3, -2, -1, 0, 1, 2, 3, like this is just I'm collected the possible difference of the left subtree or height or right subtree height. Okay, so if you are not taking absolute difference, so you may also get this type of value. Okay, negative. But if you're calculating the absolute difference, so you will always get on the right side. You will never get the negative value. So our formula, then we will only consider that this 0 and 1 value is considered as a balance.
Yes, sir. So when we move to the questions, it will be more clearer.
Okay, so this is just a representation how you are actually thinking about the balance thing. So AVL tree consider as a, if your balance difference is either -1, 0, or 1, then this will be considered as a balanced tree. If you are getting this value as a balance factor. Okay, if you are getting -3, -2, or 2 or 3 like this, so this will not be considered as a balance. In that case, you have to apply the rotation. But to save condition, if you are taking this -3, -2, and +3, +2, you have to apply more condition when you will just write implementation. So just we are making that we are just making this difference as a absolute difference. So you will always get a positive difference. So positive difference 0, 1, 2, 3 like this you will get. So these two will be considered as a balance, and other than this will be considered as a non-balance. So we will apply the rotation. So only the some condition will be changed in the code, otherwise concept is same. Okay, so I'm moving to the next question. Let's see what question is that. Okay. This is related to the okay, balance unbalanced things. Okay, just this is also related to the balanced binary search tree. So just tell me the answer for this. Which of the following statement is true about complexity of given function where n is the number of nodes? Okay, so now the complexity is given big O and log n, whether the tree is balanced or unbalanced. Which are the true about the complexity of the given function?
For what, sir?
One second.
Complexity for what?
Specifically for what? For
Uh,
searching or something?
Search, I think.
Maybe for height.
I think something is missing. Okay, yeah, this is regarding the search actually. Okay, because binary search we are looking, so every operation like searching, insertion, and deletion. So every type of operation is actually log n complexity operation. So because of that, I think this things is missed in this. So which of the following statement is true about complexity of the given function? I'm not sure. I missed or this was the missed in the question itself. So given function where n is the number of nodes. Okay, just think about the search. Okay, you can take any operation, search, insert, delete. All operation actually takes the log n time in balanced. So here this question is related to this. So big O and log n, whether the tree is balanced or unbalanced. This is not correct.
Yes, sir. For unbalanced, it can be order of n, worst case.
So big O n if tree is balanced, n log n otherwise. So this is also not correct because n is not possible for balanced tree because that we will get the log n time. Balance means I hope you know that what is the meaning of balance here. So balance you will get like this type of tree where the height is approx same on the both sides. So in this way you will get the log n steps for any type of operation. Okay, so log n means height. Okay, for n nodes, and the same n nodes you can you may also get this type of situation if your order, if you're getting this type of order to insert 1 2 3 4 5 6. So this is just like a worst case situation. So all nodes we can, all node will connect like this. So here n nodes means height will also be equal to n. Okay, so in that case you will get a worst time for the searching, insertion, and deletion. So this is also not correct. And big O n, whether the tree is balanced or unbalanced, this is also not correct. And
Sir,
log n.
can you move to the previous question? Question number 2.
I think some operation is missing, so the no operation is correct.
Yeah, I think this is the sub question for second question.
Actually, it's written question 3 based on question 2 implementation.
Oh, okay, okay. That heading I missed. Okay, okay. Okay. Yeah, so this was just a traversal. So traversal takes order of n. Yeah, sorry, I missed. So traversal means we are just traversing each node at once. So means n nodes are there in the traversal. So order of n time is fixed actually. So in that case, it doesn't matter this is a balanced or not balanced. You, this algorithm will take always order of n time because you are traversing each node. Okay, so if your n nodes either suppose like arranged in this way or maybe balanced way, you will traverse each node actually. So that means n step is minimum required in the all type of situation. So yeah, so for this, in this implementation way, then answer we have another answer. So here answer is there. Then yeah, C. I completely missed. Okay, so this C is big O n, whether the tree is balanced or unbalanced. So your this traversal algorithm basically traverse each node. So n nodes are there, then n steps is definitely required. Okay, it doesn't matter. So how the tree is arranged. So all A, B, and D is incorrect, and C is correct for this. And next is okay. So here also I'm just telling the base case. So base case is not mentioned in this question. Otherwise you will see the base case most of the question. So like here base case, why we create the base case, let me tell you. So here we are talking about the tree. Okay, so height calculation is also depends on the base case, otherwise this formula may be different. So if we are considering empty tree, so what is the height of empty tree? Generally zero height we will consider. Okay, so that like empty tree height is 0. Okay, if your tree contains only root node, single node, okay, so then height of that is 1. Okay, then we will just check the heights for formula for the remaining part if we have the tree contains some nodes. So this type of base case is generally given in the question, but in this question it is missed. So consider that this situation when empty tree height is 0. Okay, so this is just a base case for this. Now just use this base case and identify that what is the correct answer for this. So first option, the number of elements in the tree is at most h.
At
No.
least.
At least h.
At most h is not possible. Okay, so height is given here and number of nodes is at most h. This is not correct. Okay, suppose height is given like 3. So what is the maximum nodes for this height tree is? So that is
Left
not
to the left, right.
3. Okay, so that means for height 3, if you just draw quickly this, so height 3 means this level tree will be there. Okay, so this is the height 3 actually. The height of this tree is 3. So you can see maximum how many nodes this contains. So 7.
2 power
7.
3 minus 1.
Huh. So what formula will be fit for this? Okay, so this with this base case. So that means 2 to the power h minus 1. So this formula is calculated. What is the maximum number of nodes for h? So you can directly use this formula. So here the number of elements in the tree is at least h. So this is
Yes.
2. Okay, because that is the situation when your node is connected like in one path. Okay, so here height is also 4 and number of nodes is also 4. So this is the situation when h equal to n. So this is true. The number of elements in the tree is at least 2h. This is also not correct because previous was correct, so that this is not correct. The number of elements in the tree is at most 2 to the power h minus 1. This is true. You have seen. Okay, if height is given, the number of node maximum is possible 2 to the power h minus 1. So that means if height is 4, so 2 to the power 4 minus 1 means 15 node will come. You can also validate this with the help of just quickly draw with the smaller h value.
So this is always true for a binary tree, right?
Binary tree, this is always true. Okay, and the number of elements in the tree is at most, this is not correct. If previous is correct, this is not correct. So 2 we got the correct, so this was correct. And last option, this is just like a some checking process. In a binary search tree, if the number of nodes with 0 child node are n naught, number of nodes with 2 child are called as a n2, and then n0 is equal to n2 plus 1 is always true. Okay, so I hope you got the this is
Sir, I think this
statement.
works for balanced tree only.
Okay, let's see this. Okay, and see the proof for this. Okay, so what this question is saying actually, suppose if we have binary search tree. Okay, this is a binary search tree. I'm just making some more. Okay, like this. So here this is saying n0 is represent the number of nodes which have 0 child, means leaf node. Okay, so that node is just representing by a n0. Okay, n2 is representing the number of nodes which have 2 child. So like this, okay, this 2 child, this 2 child, this is called as a n2. n0 was the leaf, so this one, this one, this one, this one, these are n0. But another is possible, n1 is also possible, number of nodes with one child, so like this. Okay, so all type of nodes are possible in this. So now we can solve this with some like conclusion. So how we can prove this? So question is just like given as a let me check again. N0 equal to n2 plus 1. So this we need to check. This is always true or not. So how we can do this? Suppose we have n node in the tree. So this is representing total number of nodes. So this we can consider that the number of nodes is always equal to n0 plus n1 plus n2. Is this true?
Yes, sir.
Correct? Okay. So this is the one expression we are getting, because total number of nodes will be if we will add all these counts. And another is possible. So you can see if you see number of edge, if you have n nodes, how many edge will be there in this tree?
n-1.
n-1.
Correct, n-1. Okay, so now just look from the edge side. So n minus edge, one edge will be there. So how many edge are connecting from this n0 nodes?
n0.
So we can just write 0 into n0. I'm just asking to edge which is connected lower, okay, bottom side. So leaf node, there is no edge connected to the bottom side. Correct? So that means this count is not representing any number of edge.
Sir,
So I can write.
You mean out degree?
Number of edges, right?
Out degree, or you can say the child, number of childs. Okay, so that is representing the edge also.
So n-1 will be the minimum number of edges, right?
So these are the edge possible in the tree, or for n nodes where the n nodes are there, only n-1 edge is possible, not minimum. Okay, not minimum, maximum. This is the only possibility.
Okay.
If you have n node in the tree, then definitely n minus edge will be there. Okay, so now we are looking this expression in the terms of edge. So now n-1 edge are there. Okay, now we are calculating the edge with the help of this value n0, n1 and n2. So 0 edge are connected, 0 child nodes are connected with these n0 node number of counts. Okay, leaf node, there is no child connected actually. Plus how many edge is connected below on this
One.
n1? So
One
we can
and
write 1 into n1
Yes.
plus how many edge are connected
Two
with
into
this 2 and 2. So 2 edge are connected, so 2 into n2. This is the second expression. Is this clear?
Yes, sir.
Okay, so just look this example. So how many edge in there is for the above tree? So 1 2 3 4 5 6 7. Okay, 7 edge is there. So now just count how many edge are connected below to the leaf node? 0. Okay, so 0 plus how many edge are connected with the one child? So we have the count of nodes which have one child, only one. Okay, so 1 into 1 plus how many nodes which have two child, means two edge are connected to below them. So 1 2 3 3. So 3 into 2. So you can see you are getting 1 plus 6 7. 7h. So the same way we have calculated here. So we can write this expression like n-1 equal to this becomes 0. So n1 plus 2 n2. Okay. Now just make equal this. Okay. So just pass this 1 to this side and just write this expression like this: n0 plus n1 plus n2.
Sir, how you got 1 into 1, sir?
1 into 1. Okay.
That
So in this tree, which the tree I have drawn here, so
Yes, sir.
just figure out that how many nodes which have one child.
Oh, one child, sir.
One child. One child means one edge is connected below them, na?
Okay.
So we are looking for the one edge.
Okay.
So n1 plus 2 n2 and that plus 1. Okay, so I have just taken this one this side and put this n equal to this expression. So now just solve this. So n1 disconnected, and now n0 equal to, and this n2 you can subtract this n2. So 2n2 minus n2 only plus 1. You got this? and this was the proof. So this is always true actually. Okay, so this property is always true for any type of binary search tree, not just only strict or something. I hope this is clear. Any query in this?
Sir, how are we verifying that this is always true?
Sir, N0 means number of nodes without child, sir.
Without child.
In that diagram, how many are there, sir?
4. So 1, 2, leaf node, all leaf node, 4. So you can see 4 equal to how many childs you have with 2 children? So 3. Okay. 1, 2, 3.
Yes, sir.
Okay, getting through. So we have proved this. We have just figured out the total. We have figured out that this n value is equal to total number of counts if we calculate. Okay, so nodes with 0 child, nodes with 1 child, nodes with 2 child. So this is equivalent to n. And in the terms of edge, we have calculated again. So we have total number of edge n minus 1, and we have calculated the connected edge with every type of nodes. Okay, so 0 child nodes and 1 child nodes and 2 child nodes. Again, this is the another. This is also true. Then we have solved this expression and we got this. So this is just a proved actually equation. So this will always be true. Okay, you can verify this with some different types of tree. Okay, and figure out. You will not see any counter example for this. Okay, so this property is true also.
Yes, sir.
How
you got 2 into N2?
2 into N2? This one. So this one means, and this is N2 value is representing number of nodes with 2 childs, correct? And we are calculating this value in the terms of edge, how many edge they will produce actually. So number of nodes with 2 childs means each node will produce 2 edge below them. So because of that, we multiply it by 2. So this second expression is calculating the number of edge actually.
Okay.
Okay. So that last statement is also true. Okay, so F is also true here. So these are some basic things you can like validate with some small, make some small tree and validate that this is true or not for some examples. Okay. Otherwise, you can remember this type of some basic properties.
Sir, at most and at least when they give, what is the difference, sir?
At most and at least means, so any if you are given that height, okay, suppose h is given like a 3. So what with this height, how many maximum nodes are possible in the tree and how minimum nodes are possible in the tree? So at least means minimum number of nodes, and at most means maximum number of nodes with the same height. So if our tree is like this, so this contains the minimum number of nodes with this height 3. So height is 3 for this, h equal to 3, and n is also 3. But for the same height, if our tree is full, then here h equal to 3 and maximum n equal to 2 to the power 3 minus 1, 7. So this is the at least thing, this is the at most thing.
Okay, sir.
Okay, if you will add one more, so it will actually become a 4 height.
Yes.
So for 3 only 7 is possible for this tree. Okay, so let's move to the next. AVL tree question, where that was, let me check. AVL tree properties, this one. Okay, so I'm quickly solve this because this was the first question related to the AVL tree, and previous is also related to the AVL tree. So here you can see some inserting like sequence is given, and that how we can create a AVL tree for this. So this is also important question. So 8 4. So we will take one by one, and we will create a binary search tree. And at the every insertion, we will just calculate the balance factor for tree, each node balance factor. Okay, so now first tree is empty, 8 will insert, like, so 8 will insert. Okay, so this is just a single node, so no, 0 left subtree height, 0 right subtree height. Okay, of this 0 minus 0, balance factor is 0. So this is balanced. Now insert 4 into this. Okay, insert 4 element into this, so this will be insert like here on the left. Now calculate the balance factor of 4. So 4, for 4, left height is 0, right height is 0. So 0 minus 0, 0. But for 8, left height is 1, right height is 0. So here height, do not consider the number of nodes in the left subtree. Okay, just figure out that from that node what is the longest path on that left side, and identify the number of nodes or number of edge in that path. Okay, to calculate the height. Okay, so here the longest path is only this single path, so only one node is coming or one edge is coming. You can consider anything, but just consider the same things in the whole process. So I'm considering that number of nodes in that path, so that is 1. So left height is 1, right height is 0, so 1 minus 0, I'm writing 1 here. Okay, still this is balanced. Okay, now insert 1. So 8, 4, and 1 will be insert here. Okay, now the balance factor for this 1 is 0 left height, 0 right height, 0 minus 0, 0. Now balance factor for 4 is left height is 1, right height is 0, so 1. Balance factor value for 8, left height is now 2. Okay, this is the longest path. Okay, and right height is 0, so 2 minus 0 is 2. Now this become a unbalance. Now we required a rotation here. So rotation, what type of situation this is actually? So that is actually left type of situation. So there are 4 type of situation: left, right, left, and right. This 4 type of situation will come for the rotation. So how we are just identified this this type? So which node which have the balance factor more than 1 from the bottom side? Okay, so maybe you will get the more than one node with balance factor 2 or more than this. So always rotate first which are coming nearest from the bottom. Okay, so if you just see from the bottom, just rotate the first node which are coming first from the bottom side. So this 8 is containing more than one balance factor. So from this node, just look which side height is more, left side. Okay, from this 8, which side height is increased actually? So left side, just move to the left, children, and from the left, children, just again see which side height is increased. From the left, children, again left. So that is because of that, this is a LL situation. For this situation, just consider this as a pivot position and pull this one position on this side like clockwise. Okay, so this 4 will reach at that pivot position, and this will become, this 8 will rotate here and 1 will rotate here. Okay, now this become a balance. So 0 left, left 0, right 0, 0 minus 0, 0, left again same. So always leaf will be considered as a balance factor 0. Okay, now this 4, left height is 1, right height is 1, 1 minus 1, 0. So all are now become correct. Now insert the next element in the balanced tree. Okay, which we have make balanced after rotation. So this 3 will be insert. The 3 is less than 4, greater than 1. So I'm just writing here. So now 4 and 1 and 8. Okay, so 3 will be insert this side. Now balance factor for 3 and 8 is 0. 1 is 0 minus 1. Okay, so 0 left height, 1 is right height. So in this case, you will get minus 1. But we can just follow this process with the absolute value. So I'm writing 1 difference. Okay, 1 difference here. So now same for 4. So left height is, what is the left height here? The longest path is 4, 1, 3. So 2. 2 and right height is 1. So 2 minus 1 is 1. You can see all are coming below 2. So this is balanced. Now 9. So insert 9 here. 8. So 9 will be greater than 4 greater than 8, then it will come here. So again 0, 0, this 0 minus 1, 1, and 0 minus 1, 1, and 2 minus 2, 0. You can see still this is balanced. Okay. Now insert 2 in this. So I'm just writing 4, 1, 3, 8, and 9. So 2 is less than 4, greater than 1, less than 3. So you can see this situation we are getting now. Now 0, 0. So sorry, what I have written wrong? 2. This is 2. So balance factor for 3 is 1 minus 0. So 1. Balance factor for 1 is left height is 0, right height is 2. 2. Okay. And what is the balance factor for 8? 0 minus 1, 1. What is the balance factor for 4? 3 minus 2, 1. Okay. So you can see we are getting this node as a unbalanced 2. Okay. So what situation now we are getting this time?
Left, right.
No,
Right,
not
left.
left, right. Right, left.
Right, left.
Right, left.
Okay, from this one, which side height is greater? Right side. Okay, so first.
Sir, how you are saying right, left? Sir?
So I'm telling you on the node which have the balance factor more than 1. Okay, so we are looking from that node. Which side height is increased?
Right
Right
side,
side.
right.
Right side, na? Left height is no. Actually, nodes are there. So right side height is increased. After that, just move to the right child, just right child of that node, and from the right child, just look which side height is increased from the right child. Left.
Yes.
Okay, so this is left. So this is RL situation. RL situation. So for RL situation, there are 2 rotations required. First rotation we will apply it on the childs. That is actually clockwise rotation. Okay. After that, next rotation will be applied on the node which have the balance factor more than 1 on anti-clockwise. So 2 rotation will apply here. So like 4, 8, this will remain as it is. So after first rotation, you will get like this. So this part will be rotate actually. So this part will be rotate clockwise. So 2 will come here and 3 will become here. Okay. Now after that, next rotation will be applied on this one, that is anti-clockwise. So you will get 4, 8, 9, and then 2 will come here and 1 will move on this side, 3 will come here. So 0 balance factor 0, 0. Now for 2, 1 minus 1, 0. For 8, 0 minus 1, 1. For 4, 2 minus 2, 0. So all you can see all become now less than 2.
Sir, can you write what is the rotation required for LR and RR?
So that I think that is given in the notes. If you have not seen, I'm sure. Okay, 1 second. So I'm removing this. So I think let me check the any additional rotations is required or not first. So what are the notes remaining we have? Let me complete first this. Okay.
11.
11. So 11 will be added after this 9, but that will that will also actually change the things. Okay, I'm just making the ever. So because this is screenwriting, will not delete this. So 9 will be 11 will be connect on the right side of 9. Okay, after that I'm just getting these things. So like 4, 2, and then 1, 3, and then 8, 9, and then 11. Okay, so this is 0, 0, 0, and this is 0, this is 1, this is 2, and this side 3 and 2, this is again 1 only. So you can see we got this part actually unbalanced. So this is the situation of right. Okay, from this 8, which side height is increased? So right. Then from the child, which side height is increased? Right. So for that, only one rotation is applied on the
Anti-clockwise.
8, that anti-clockwise. Okay. So only this part will be rotate, like 2 and 1 and then 3, and then 9 will come at above, and 8 will come this side, and 11 will come this side. So now this become a complete tree. So what are the nodes which are coming on the leaf? 1, 3, 8, 11. So 1, 3, 8, 11 is the first option. Okay, so this is the idea of the rotation. So let me just quickly tell you the what type of rotation we applied. So I am just removing this. So for RR rotation, so R rotation, so no, first starting from LL. So left rotation, so like this type of situation. Okay, if you are getting this type of situation, left at any part of the tree. So this type of rotation, so means this is the initial node where actually we are getting the balance factor more than 1, and this is LSHS. So at that time we required a one rotation on this node clockwise. So okay, suppose this is A, this is B, this is C. So this will become a B top, A here, and C here. This is the LL. RR, if you are getting like this type of situation, A, B, C at any part of the tree. So suppose this is 0, this is 1, this is 2. Okay, so in this situation, this is RR. So apply the rotation on this node, and that is anti-clockwise. So B will come at the top, A will this side, and this is C. Okay, now for LR,
Sir, then how is it left rotation? You're rotating it towards right.
no, on the LL part, this position is a pivot position, and just like a pull these things. Okay, pull one position to this side, anti-clockwise.
You're pulling to the
So
right.
so B will come at that position, and A will shift on the right. So this type A. And for this RR situation, just make this as a pivot position, A position as a pivot position, and pull this side like. Okay, so B will shift here at the A position, A will shift on this left part, and C will just shift one up position. So this is just like, okay, LR is a situation when you are getting A and then B and then this side C. So left R, like 0, 1, 2, this type of situation. This type of situation, first rotation is applied on this position. Okay, just make this B as position as a pivot position and pull this side like this end. Okay, this side. So you will get a one, after one rotation, you will get a C and then B. After that, second rotation will be applied on A, that is clockwise. Okay, so C will shift at the A position, so C will come here, A will become down, and then B. This is the one. And RL just the reverse of this. So RL, your if is A, then B, and then C. Okay, so this is R and this is L. The first rotation will be applied on B, and that is just a clockwise. So after one rotation, A, C, and B. And next rotation will be applied on this, so that is anti-clockwise. So C and A, and then B. So these are the four rotation, and one situation is there in the any type of rotations. Suppose you are getting like this type of situation: A, B, and C. I'm just making a random thing. So like this is okay. So suppose if I am just making this D, E, F, I'm just connecting here. Okay. So till that point, just remove first here. Till this situation, you can see we are getting, why is it not deleting? So till that point, you can see balance factor for this is 0, this is 0, this is 0, this is 0, this is 1. Okay, 2 minus 1. Okay, but suppose if we add one more node here, like F, then this balance factor will become like this is 0, this is 0, this will become 1, and this B will become 2 minus 1, 1, E is 0, and A will become actually here what? 3. Longest path is A to F. Okay, this is 3, and this side 1, so this will become 2. So this type of situation you will get. Now you are getting this 2 balance factor on this node. correct? So from that, just see what situation this is actually. So left side, which side height is actually more? Left. From the child node, which side height is more? Left. Okay. So LL situation is this actually. So means we required a rotation on this node to clockwise rotation. So for this type of situation, because this is just a root position, okay, where we are actually rotating. So this B should be shift at A position and A should be shift to the right. So means if we just rotate one position like this, so B will come at this A position and A will be shift here and E will shift one more down, and now D will shift one up and F will shift one up. But here this C was connected to the right of B, but now B is reaching at the root position. So B has the right child, B has the left child, but where actually C should come now, which was previously connected to the right. So for this rule, actually, if B are reaching at the top position, okay, now A is already become a right child of that, but C was previously connected to the right. So this C is actually become a left of this A after rotation. So this C will come at here. And now your binary search tree property will be preserved if you make this. So this is just some handling situation if you get this type of situation for any time. So B will come at the A position. So this, if any node is which is coming on the right side of this C, so that will become a left of A. So this situation may become on the other side also. Okay, so that you have to make differently. So like this type of situation, if I just make A.
Sir, that we can see the value on place itself.
Value of? So I'm just putting. No, you cannot directly connect in any place by your own. So that is some rule actually in the AVL tree that you have to follow.
No, sir,
So,
that value, no, sir. C
value.
will be greater than B and less than A. Similarly, here also C is greater than B, less than
Yes.
A.
Yes.
It will automatically come to that place only, sir.
Automatically connect, but maybe sometimes if you maybe connect on the some different place to make just a balance, just for some one instance. Okay, but here this, if you follow this rule, you will always get a one binary search tree after this allocation. Okay, so where this key should be connected.
so like you are saying, for LL you have to rotate clockwise.
No, rotation we are doing in the same way. The here difference was there. After rotation, this B is coming on the top. By default, this A is connected on to the right of B. Now where actually this C should come actually, because C was previously right connected to the B, but there is no right position is available here. So because of that, we have arranged this actually C to the previous root node, which has now shifted to the right and to the left. Otherwise,
It is a clockwise, no?
This is the clock for LL rotation. We apply the clockwise rotation, na? So that I have already discussed ever. So LL means clockwise rotation on the node. RR means anti-clockwise. LR means first rotation is anti-clockwise, then second rotation is clockwise. So you have to just remember these rotation actually, and that you can remember with some practice. Just take some sequence and just create a wheel tree and apply this rotation, then you can remember. Okay, so the similar type of situation may come on the different side. Suppose this is A B C D, this is connected like this, A B C D E. Okay, this is just a balance, but suppose if we add one more here, so this time the situation is just different. So you will get 0 0 1 and 1 and 2 and 0. Okay, so now you got this. So this is RR situation. So this time anti-clockwise. Okay, so B will come at the top now. A is shifted here. So D and C and then F. Okay, now this E which was connected to this B left, that is now become a right of A this time. Okay, so this is just one additional condition will occur at the time of rotation. So just remember this situation. Okay, so this is the ABL tree rotation. So you can just do some practice on a 3, for example. You will learn this.
Sir, I have just shared image. If it says for LL, we have to rotate anti-clockwise.
What rotate?
Um,
So same things I am saying. What is the different things I am saying here? Oh, LL rotation.
yeah.
Here, this actually considering some different meaning of LL rotation here. This is we are talking about the situation, and I think not looking this is not looking correct.
Sir, actually, they are trying to rotate at position 2, not at position 1, which is wrong.
No, this is applying the anti-clockwise rotation, but this is giving the name to this LL rotation. So I'm not sure this is thing. But instead of name, you should know what is the situation actually. Okay. To make balance, what is the situation you are getting? You are getting to the left side, like left side high. So maybe this is giving the name according to the rotation. Okay. So what type of rotation we are applying? But we are giving the name based on the like which side actually our tree is unbalanced. So based on that rotations we are applying the same type.
Okay, it's only the naming convention which.
Some maybe this is taking the some different naming convention, otherwise the rotation this is also same. I'm not sure, but this is LL rotation is I think not correct. I'm not sure where from you are taking. Okay, but just remember how we are applying the rotation, what type of situation we are applying, which type of rotation. So that is just the main important part. Some naming convention is some maybe different. So because of that, some height problem, na, so which I have just mentioned, we just generally consider the height is actually equal to 0. So empty tree we generally consider height is equal to 0. Sometimes you will get if single node is there in the tree, they will consider height is actually 0 for that. Maybe some books you will see if single node tree is there, they will consider height is 0. Okay, and maybe some another book, if no single node is there, they will consider height equal to 1. So this type of convention may be different. Accordingly, you have to validate your formula. So for this situation, your formula will become different. So for h equal to 3, then what will be the number of nodes? So here you can see, so this will become a 1 height. Then this will become a like 2 height. Then this will become a 3 height. So for this convention, you have to apply the formula in different way if this base case is given. Okay, for this base case, we are just taking this as a height 3. So you can just validate this. Suppose if this is given as a base case, so what will be the number of nodes with height 3? So you have to change your formula like 2 to the power h plus 1 here like this, h plus 1 and minus 1. You have to write like this. Or for this situation, you have to write 2 to the power h plus 1. Not, sorry, minus 1.
Sir, this is for ABL training, right?
Any binary tree, any binary tree. So this is just a different convention to represent in different resource. So here some the base case is different. So that because of that formula will also be changed for maximum number of nodes. So because of that, most of the time we generally gives the base case. So accordingly to you select the correct answer for the height. Suppose if we are considering that height is equal to 1 for single node. So means this is the structure for h equal to 3. Okay, so for this validation, you need to follow this formula minus 1.
So sir, this is for complete binary tree, no?
This is for maximum number of nodes if you are calculating. Okay. So this is just a little bit convention different here. So always check the base case. What base case is given in the question? Let me move to another question. So I have made this. Let me coming to the previous one. Okay, so we have discussed till here. Okay, I'm just quickly going because otherwise we have already done 1.5 hours. Okay, for activity x comma x it v is the starting time and xe is the, sorry, this is the xs. Okay, xs is the starting time, xc is the ending time. The following are the starting time and ending time activities, abcd in the chronological order. What is the minimum number of rooms required to schedule this activity without any confliction? So here this type of question you can apply the greedy approach like this. So this is greedy approach question. So here you can just make the draw for this. Okay, so here this is just like a manual draw question. So as you can see, initial first activity you will always start from the first room. Okay, suppose if you have the first room like this one, you have started the as activity in this, because this is not end. If any other activity is coming, definitely you have to enter that activity in different room. So we will always check that if any previous room is empty or not. Otherwise, we will always enter new activity in the new room. So BS is now coming because first room is still busy. So second room you will enter BS activity. Okay. Now CS again, we don't have empty room 1 and 2. Third room we have to enter CS. Now AE, you can see AE is now ending of A activity. So A is now done. So this room is now become free. First room is become free. So now DS is coming. So we will not create a new room for that. So we will just use the first room. So DS. Okay. CE. So CE is now completed. So third room is now again empty. So ES again coming. So we can enter into third room. Okay. Now BE is finished. So BE. So this is finished. Now FS is coming. So FS we can enter here. Okay. Now DE is finished. So D first is empty. GS is coming. So GS will enter here. Okay. So EE is coming. So this is finished. And HS is coming. So HS will insert here. FE. This is empty. Now GE. So GE. This is empty. HE. Okay, it's empty. So you can see we have done all the activity minimum 3 rooms. Okay, in this way. So in this way you can solve this type of question. So what are the minimum number of rooms required? Just maintain this type of order and just check. So this is the basic general question to check the minimum requirement, and I hope this is clear. Let's move to the next. Okay, this is Hoopman code. So we have we have discussed this in much details the previous session also. So you have given one probability, okay, probability of occurrence of each character. So this time, sometimes maybe you will get a frequency, sometimes you will get a probability. So means we have one message where the A like occurs with this probability 0.22 probability. Okay, B is occurs with 0.21 probability. Okay, this is just represent the how much time actually this character is actually occurring. Okay, so now we are identifying that what are the codes for this. So how many bits will we use to encode the message A B C D E using Hoopman code? So Hoopman codes, I hope you know that how we can generate the Hoopman tree and Hoopman codes. So we always picks the smaller 2 probability and then we will make that as a Hoopman tree. So here what are the 2 smallest ones? 16 and 11. So I'm just marking that as a 16 and 11. Okay, so this 16 is represented C and E. So just remember that 0.16 I'm writing only 16. Okay, so make this as a 16 and 11 27. Now this is done. No, sorry. This is complete and this is complete. Now remaining is 22, 21, 27 and 30. So what are the 2 minimum next? So that is 22 and 21. So we will create a separate for that 22 and 21. Add. So you are getting 43. Okay. So this is done and this is done. Now 27, 43 and 30. So 22 is representing A and this is 21 is representing B. Now 27, 43 and 30. So this 30 is the with 27. So 30 and this is representing D.
Sir, first we have to arrange everything in the ascending order.
So you can do this in this way. Otherwise, you can figure out the two smallest one. Okay. So I'm doing the same things every time I'm selecting two, or you can do this with the process of sorting. So always select the first two. So now 27, 30. So this is become 57. Now 57 and 43 we will directly add. Okay, 100. Like this. Okay, now we'll make left 0, right 1. 0, 1, 0, 1, 0, 1. Okay, now calculate the code. So for A, just traverse from root to leaf. Okay, that A. So we are getting 1, 0. Okay, by this path. For B, we are getting 1, 1. For C, we are getting 0, 0, 0. D, we are getting 0, 1. E, we are getting 0, 0, 1. Okay, so if you are traversing from root to that node, you are getting this codes. So for A, B, C, D, E, what bits are required? How many bits are required? So just add the length of each. So okay, so 2, 2, 3, 2, 3. So 2 plus 2, 6, 2 plus 2, 4 plus 3, 7 plus 2, 9 and 3, 12. Total 12 bits are required for this message. Okay, A, B, C, D, E. So this is the answer for this. You can, in this way, you can generate the codes, generate the Hoffman tree, and figure out that the length of the each code. Okay, and sometimes code is asked. Suppose that code you can represent. So based on the question, you can identify that what type of information is asking here. So this is the method of Hoffman algorithm. Any query in this?
No, sir. Thank you, sir.
Okay.
Okay, sir.
Okay, so next is this. Okay, here insertion or order is given. Empty by insert tree and element at the maximum depth are. Okay, so quickly create a maximum tree for binary search tree for this. Okay, so this is binary search tree. So 50 will be become root. 80 is greater than, then 80 will add here. 20 is smaller than 50, so 20 will add on the left. 60 is greater than 50, less than 80. 60 will add here. 10 is less than 50, less than 20. 10 will add here. 45 is less than 20, less than 50 and greater than okay, so 45 will add here, and 65 is greater than 50, less than 80, greater than 60. So 65, and 30 is less than 50, greater than 20, less than 45. So 30 will add here. 90 is greater than 50, greater than 80, 90 will add here. So sum of the elements of the elements are asking. The element at maximum depth are, so maximum depth is this one. Okay, so 30 and 65. So this is coming at the maximum depth. So 30 and 65. So okay, so this is the answer for this.
95, sir. Some
90 is coming. So depth is considered as a from the root node. So this is coming 0 depth. This is coming 1 depth. These okay, this level you can consider.
okay, it is
next
asking
level-
elements.
So elements which are coming on the maximum depth too. So this is are coming at the third maximum. So 30 and 65. So this is the solution for this question. And next is okay. So these are some properties of AVL tree. Just quickly see and tell me the answer for this. First property is given. Let SS denote the minimum number of nodes in an AVL tree of height h. Then SH equal to SH minus 1 plus SH minus 2 minus 1. Where S0 equal to
It
0
should
and
be
S1
plus
equal to
1.
correct. Okay, so for AVL tree, so suppose this is the one node, single node, which is balanced actually. Okay, so we are considering that this is the h equal to 0. This is the balance. For H1, what is the minimum actually number of nodes possible? So this is the situation like this. This is will be considered as a balance, but this contains the minimum element. So this H1 equal to no sorry H0 is equal to empty, H0 equal to empty, H1 equal to this one single node. Okay, so if this is one, if we want to make H2, so we have to combine this, so we can calculate like, so this is the situation. For H2 you can connect like this. So means what is the height of empty tree plus what is the height of single node plus 1. So we require in this way. So always just take the previous number of nodes of two heights and then plus 1. So plus is required for this. So for minimum number of nodes in the AVL tree. So here this is just like a Fibonacci type of sequence. You always, if you want to calculate the height of like S8, so you cannot directly calculate for this. You have to come from this S0. So S first calculate S0, then S1, okay, then S2. S2 will be calculated with the help of previous two. S3 will be calculated with the help of previous S1 and S2, like this. Okay, S1 plus S2 plus 1. So in this way you will reach at this. So then you can figure out. So this type of question directly come. Okay, so in that way generally smaller value we generally ask. So you can always comes from the base, and like a Fibonacci sequence, just calculate and reached at that point. So this is incorrect because here plus is required. So in AVL tree, the absolute difference between the height of the left subtree and the height of right subtree of any node can't be more than 1. So this is true.
This is true.
Okay. The complexity of searching in AVL tree is log n. Because AVL tree is balanced tree, so this operation will be performed in log n. If the height of an AVL tree is h, the maximum number of nodes will be 2 to the power h minus 1.
Yes, sir.
This is correct. Okay, the complexity. So you can see here this base case is given. Okay, because of that this is true. The complexity of both insertion and deletion in AVL tree is big O n. So this is not correct because that operation can also be performed in log n times. So this is not correct. Okay, so this is done. Yeah, Huffman code. So Huffman code, which I have created previously. So we have generated the Huffman code. So there is one property actually. So here this question is asking which of the following are possible valid codes for the character set S, A, B, C, D, E, F, generate using Huffman algorithm. So there is one property comes in the Huffman codes. The codes are prefix codes actually. That code generated are actually prefix code. Means any code cannot become as a completely prefix of any another code. Okay, so you can see this validation on the each code and identify that this is possible codes or not. So here you can see 0, 1. Just always look from the smaller code and see that is coming in the another big code.
This is the prefix of same.
So yeah, so you can see 0, 1. 0, 1 is coming in the prefix. Yes, this is coming. So this is not possible in the main codes. So here again, see 0, 1 is not coming, but 1, 0 is not coming, but 1, 1 is not coming. So this is like looking correct.
Sir, 1 is coming in C, no, sir?
No, that is coming at the end, but prefix means in the initial part. That means from the starting part, that should not become. Okay.
Sir, 0, 1 is coming now, sir.
Which one? 0, 1.
Sir, 0, 1 in B.
0, 1 is coming in which one?
B, sir.
B. No,
Yes.
no. This is coming in middle, na? I am just talking about the from the initial actually. First,
Okay.
That is called
First
as
to
a
come.
prefix.
Okay, sir.
That is called as a prefix. Okay, suppose if A, B, C, D is written here. So here A is a prefix for this, A, B is a prefix for this, A, B, C is a prefix for this. Okay, so this part is coming in the initial, this part is also coming in the initial part, this is also coming in the initial part, but we cannot say that this BC is a prefix for this. Okay, BCD is a prefix.
Okay, got it.
Okay, this is called as a prefix. Now the C option, you can see like 1001 is not
E is the
coming.
prefix of B.
Coming. Okay, yeah, you can see E is coming here as a prefix. So this is not possible. And in the last option D, so the C00 is not coming. 1010 is also not coming. Otherwise, all three actually, three characters. So that is also true. Possible.
Sir,
Hmm.
what if two characters have the same prefix code?
That is also not possible. You can also like check this. If
That cannot
two
work.
characters are two same, you can mark as a invalid.
Sir, B is 010, sir. C is 011. Shall we take it as
010. 1 second.
011?
B is 010 and
next one is 011.
that is given now. So this is possible.
This is not prefix, sir.
No. You are saying B is 010 and C is 011. So this is how this complete code is coming in the prefix. It is not coming now. Same length code cannot be a prefix of any other.
Okay, sir. Okay.
If both are not similar. So because of that, we are looking for the smaller part. So 00 can maybe prefix of anything, but this in this D option, this is also not there. Then 10 is also not coming. So that is true.
Sir, just a bit curiosity, like why are they called prefix codes if we are not concerned about?
So that is just some definition things. If we call it as a prefix code, means any code is not a prefix of another codes.
Yeah, so then why are we saying prefix?
That is just predefined things, so that we have to. Okay.
It's like just opposite.
So this creates some confusion a little bit. So prefix code, we think about that code are prefix of others, but that is not the case here. So prefix code means that any codes are not a prefix of another codes. Okay. So moving to the next. This is again scheduling problem. So this, suppose you know the process. Here some meetings are given, start and end time is given. We need to find out that how many maximum meetings we can schedule without overlapping. So how we will solve this? If you remember which algorithm it is representing, which we have seen in the Week-7.
The interval scheduling, sir.
Interval scheduling. And what is the process for that? How we solve that?
Earliest deadline should be chosen.
Yes, sir.
So
ascending order. We have
so we just arrange these meetings based on this end time in increasing order, and then we pick the from the starting. If our starting time of any meeting is not before the end time of the previous selected one, we will select the next. Okay, so this is the only approach. So in this end time, just see which one is coming the smallest. So this 3 is coming, so this will be selected as a one first. Okay, M2 is selected. Now next one is which one is the next greater?
Sir, there are no deadlines, no? Here. This is interval.
This is the different problem. This is the interval scheduling problem.
Yeah.
That was the maximum lateness problem, deadline one.
There are finishing times.
So this is end time here. Okay, based on that end time, we will sort that and we will take that. Okay, so 3, next one is the 5. So you can see we will pick this, but before that we will check if the starting time is not before the previous end time, previous selected end time. So here we can, according to the definition, if any activity finish at time t, then other activity can start at time t or afterwards. So means we can select this because both are same. So this one also be selected. Next one is 7. So 7, either you can see this and you can see this both. So suppose we are looking of this M1. So 7, but starting time is 4, but which is smaller than previous end time. So we cannot take this. Same for this 7. Starting time is 2, which is smaller than the previous end time. So this we can also not take. Then next one is 8. This one. So starting time is 6, which is greater than the previous end time. So this will be selected. Now end time is 8. Next greater is sorry 9. So 9 starting time is 7, which is smaller than. So this cannot be taken. And this cannot be taken because 6 is smaller than 8. So this also cannot be taken. Now next is 11. So 10. Yeah, 10 is greater than 8. So we can take this. Next. Now end time is 11. So we will select next is greater than. So this is 12. So this we cannot pick. Okay. So because 9 is smaller than 11, but this we can pick. Okay. Because this is starting from 11 to 12. Now end time is become 12. So next one is this one 13, 15. So again, this is starting after the 12. So this will also pick. Okay. So how many we have selected? 1, 2, 3, 4, 5, 6, 7. This is also no, this was removed. Sorry. This 3, 4, 5, 6. Total 6 we have selected. Okay, so M2, M3, and M5, 7, 8, and M11. So maximum 6 meeting we can schedule. This is the answer for this. So you can solve this type of question based on this approach, interval scheduling. Okay, inversion pair. Now week 8. So from week 8, some questions are generally comes on this inversion pair things. So here this question is asking the maximum number of inversion pair possible in an integer array A of size 15. So 15 elements are there. So I hope you remember the formula.
N into n minus 1 by 2.
So 15 into 14 divided by 2. And you can calculate this. Okay, so I think 85. So 85 is the answer for this. This is the maximum. Minimum is 0. Okay,
So
maximum.
it's 105.
Sir, what is the formula? Can you write?
N into n minus 1 divided by 2.
What?
What was the multiplication? Oh,
Sir, it's 105.
105. Okay, yeah.
Yeah, that's what I
105. Yeah. Okay, so maximum is this. Minimum is 0. Otherwise, if any sequence is given, you can simply calculate manually. Suppose any sequence is given. Sometimes 2 order will be given, and you have to relate it to that. So, like suppose if suppose this 3, 5, 1, 6, 4, 2. Suppose this order is given, okay, and find the inversion pair. So simply you can see by the each element how many elements which are smaller than this and coming after this. Just count that. Okay, so for 3, 1 and 2. Okay, so 2. And for 5, 1, 2, 3. So 1, 4, 2 are smaller than this and coming after that. So plus 3. For 1, 0. Okay, for 6, 2. Okay, plus 2. For 4, 1. So just look on the right side only and see how many elements are smaller than the current element. And that are the actually inversion pair. So if any single order is given, so we will just always relate with the sorted order. So 1, 2, 3, 4, 5, 6 with this. So you will get this inversion pair totally 8. But sometimes what happen if 2 orders are given, A or B, and question is asking about the inversion pair among them. So that means so suppose one order is given like 5, 2, 1, 3, 4. Okay, and another order is given. So this is A, and suppose this is B. So like 4, 1, 3, 2, and what is even 5. Okay, suppose this is the second order. And now we are asking that what is the inversion pair of B correspond to A. Okay, so that how we will figure out. So just here we will apply the mapping. Okay, so just map this with the sequence order. So 1, 2, 3, 4, 5. Okay, I've just written like this. I've done the mapping, and now on the similar basis write the sequence for the B. Okay, so 4 is just mapped with 5, so just write 5 first. Okay, 1 is mapped with 3, so 3 right here, and 3 is mapped to 4, and 2 is mapped to 2, and 5 is mapped to 1. Okay, so this sequence now compare with the sorted sequence, this one, and just figure out that how many. So you can directly check this with the same previous logic. So for 5 totally 4 are coming, plus for 3 2 are coming. Okay, for 4 2 are coming, for 2 1 is coming. So now this is the total number of inversion pair for this question. Okay, 9.
Sir, it is with B with A or A with B? What is the
Inversion pair for B correspond to A. Okay, if question is asking what is the inversion pair for A correspond to B, so then just map the B and check for A.
Okay, sir. Okay, sir.
Okay, so this type of question generally comes. So okay, so this is MOM algorithm. So one possible question is also asked in the MOM. One sequence will be given. So this is some different complexity means. So using MOM, the worst case running time of the kth largest will be n. So is this true?
No, sir.
So this is true. Okay, so we have already see the algorithm fast select, where we are using MOM algorithm, where we are achieving our like kth largest or smallest element in log n time. So this is true. Using MOM, the worst case running time of the kth largest element will be n log n. So this is not true now. Using MOM, the worst case running time for quick sort is, yeah, this is true, because we
Yes.
can improve our quick sort complexity in n log n. This is true. So 1 and 3 is correct. See. But for this MOM algorithms, generally this type of question is also asked. Some sequence will be given like 1, 5, 3, 6, 8, like long sequence will be given. And suppose we are asking the question using MOM with block of 5 elements. So how you can do that? So how you can solve that? What is the median element generally that asks to calculate the median element for the sequence? So just take 5 element from the given sequence. Okay, and sort each block. Okay, suppose you are taking the first block, so sort each. Okay, so 1 3 5 6 8. So in this way sort each block then. Okay, how many blocks you are getting, then check the median element. Okay, so median, just pick all the median element from the all block. If those elements are again coming more than 5, okay, or like 3 or 4, again select the minimum element among. Okay, suppose you are getting 5 element all medians, so 5 medians total. Okay, then pick the median of that again. So in this way solve that problem. Okay, so if a problem is given 5 block problem, so just make the 5 blocks. Otherwise sometimes 7 elements blocks person also asks with this, so make the block of 7 or each, then calculate this. So this is the problem. Okay, so we have seen this, so we can directly calculate this. So 1 4 1 0 for 4 2 plus for 3 only 1, for 6 2, for 2 0, for 5 0. So total 5 inversion pair. I hope this is very simple, straightforward.
Sir, hello.
Uh-huh.
Sir, in previous question,
Hmm.
the selecting kth largest,
Hmm.
it should take the complexity 1
No. How you can identify the kth largest in one time?
by indexing, means it is sorted in
No,
descending or
it is not.
ascending.
No, it is not. It is a random list. It is a random. Okay, so like 3 1 5 6 2 7 8 9, like this, and we are finding the fourth largest. How you can identify this?
Sir, how many questions are left?
We have total 19 slides, so 13 is going on. 5 6 are remaining. Okay,
Yes.
so this is done. This is done. Okay, now this is the important question from B8. So some recurrence relation will be given, and you have to figure out the complexity for that. So we have discussed this also in the previous session in detail, recursion tree, how we can identify that. So for just tell me which recurrence relation you have seen in this. You can directly identify the complexity.
C and D we can directly say.
For
C is
the
order of n squared and D is log n.
Okay. So for this situation, any example you have seen for this?
worst
With
case of
quicksort.
quicksort
Huh.
without
Correct.
money.
So quick sort worst case. Yes, this is the example for quick sort worst case. Okay, so in this case we are getting this n square. But and for this, any example?
Binary search.
Fast select.
Yeah, binary search. Fast select is not, because fast select big O n is there. Okay. Here this part is actually big O n, partition process. But this is actually a binary search.
For binary search, there is two, no? Two into two.
No. Binary search
No,
only
that is
one.
merge sort with order of n.
So binary search only one recursive call is required. Okay, on the either left half or right half, and one step for comparison. Okay, but for fast select, one call is required, but for partition, n step is required additionally. Okay, only the difference is this. So for this, log n complexity is there. So now this recurrence, how we solve this? So 2t n by 2. So for recurrence relation, I hope you remember we have done this.
So we can use master theorem just for solving purpose.
If you know master theorem, you can also use that, but that is not, I think, covered in our course. So, but if you know additionally, so you can use any things.
Sir, it is there, no? In week 8.
No, recurrence relation, recurrence T is discussed. Master theorem is not covered.
Isn't it master's theorem?
No. That is recursion tree. Okay, so for this recurrence relation,
the methods are given, no? Like for increasing case of
that type of recurrence tree actually we have seen. So for this, if you make the recurrence tree, so Tn is now additionally you have n operation. Next time you have total 2 call. Okay, so first call and n by 2 step is required at this call. Okay, and n by 8. Sorry, n by 8, n by 8. Okay, if you add both, so you will get it 2n by 8. So means n by 4. N by 4. Next again 2 call will be there, and that will be n by what, 64? 8 n by 68, 64, n by 64, n by 64. Okay, n by 64. And if you will add, so 4n by 64, then you will get a n by 60. So here you can see this, you are getting a decreasing order. And for decreasing order, always this is the complexity. Okay, what complexity you are getting on the root, that will calculate at the overall complexity. If your order is you are getting decreasing operation by some factor, so just take fn equal to your complexity. So what is the fn here? So this part will become your complexity. So this will reach at this. And for the B option, so 4t n by 2. So here you can see n by 4 is there, and below n operation is there. So tn will start from the top, and n step is there. After that, 4 call are there. Each call have the size n by 4. Okay. And that is the additional time is required, because if n is the input, n step is required. If n by 4 is the input, n by 4 step is required at each. So if you add 4n by 4, so it will become n. Next step, again 4 call for each, that is n by 16, and total 16 calls. So 16 into n by 16, again n. If your operations or your cost is same at each level, then fn log n. Okay, you can calculate the complexity directly with this fn log n. So this is n log n. And if your operation are increasing, in that case, so that is n to the power
log r.
and I think CR. Recursive call, and this, I think RC or CR. Just check this one.
R base.
So
Yeah.
CR.
CR.
Correct, sir, correct, sir.
This one is correct, na?
Correct.
CR. So this is the way you can calculate. So what C is the number of that partition, how what factor we are dividing. R is just a number of recursive call. Okay, so in this way you can calculate. So recurrence relation you can solve like this.
Sir, isn't this the so-called the master's theorem?
Master theorem is also similar, but that the approach is different. Where we not generate the tree, we not looks the tree, and there is some formula A, B, C value you have to calculate. Then some conditions are given, and based on that you have to conclude. So that is also similar type of approach, but mathematically.
But then this formula is same, no? Like for increasing.
These things are same, but you have to figure out that which type of situation you are getting. So 3 cases are there for master theorem also. So based on that you have to conclude.
Also, sir, for just the thing, only we can solve A, B, and D. We can't solve C using master theorem. So for C, we have to use the back propagation or backtracking method, which you just did. The C, Tn minus 1 plus O of n.
No, what you are talking C here means?
No,
This one,
sir.
this one. Okay,
That
this
third
one.
one, yeah. We can't use master theorem for that.
Yes. Correct.
We have that
So
rule,
actually
right?
we
B
require
has to
that
be
A,
strictly
B,
greater
C,
than
that
2.
we have to relate some equation, so that we have to figure out every things. So this also recurrence tree is also required for that divide and conquer type of approach. Here also we required RC value, so this there is no RC things here. So this type of calculation is generally done by some simple substitution method or simply expand the expression. So here there is actually no divide factor here for third option. So recurrence tree is also not good for this. But yeah, we can solve this, but that will come linearly, like simple one, no T and
Back substitution would be better. For n minus 1, then n
substitution.
minus 2, then
Yes.
n minus k we can have,
So
then we can just
yes,
replace
so
it.
you will get simply same type of equation here. So Tn next call is single call, so Tn minus 1, so total n minus 1 steps, n steps. You will get a series, and then you will add that series, and you will get. So that the simple substitution method is fine for this. Okay, so that is, I think next questions are also related to only this. So this was the recurrence for first select. Okay, so what type of order we will get here? So same, we have seen this. So Tn, okay, and next step n by 2. So Tn by 2, n by 2. So you can see this is reducing at each level. So n by 4 and so in this way, this is the highest order. So we will make this as a complexity big O n. Okay, so this will become a complexity for this. Next is that is also, I think, recurrence. So this is simply merge sort or quick sort best case, merge sort all case. So this is straightforward. Cost will be same on the each level, because n by 2 plus n by 2 calls, you will get a n. Next n by 4 times, you will get a n. So this is same merge sort algorithm explanation. And this is the last. So I think this we have done. This is the increasing case. So you can see, so Tn and n cost is there, then 4 calls are there. Each calls have n by 2 cost, total 4n by 2 means 2n. Okay, next time this will come n by 4, and total number of 16 times. Okay, n by 4 and 16 times, 4 for each. So 16 into n by 4, so 4n. So you can see this time it is increasing. So what terms we will get at the last level, so that will be actually the like dominate the other terms. So for this we will calculate the complexity like simply. So n to the power log, what is the c value here, 2. Okay, and what is the r value here, 4. So 4 we can write 2 to the power 2. So this will come here. So n square, and log base to 2 value will become 1. So this is n square. Okay, so this is big O n square. So this is the solution. Okay, so all done. So if you have any query from these questions or any other question, you can ask now. Any doubt, any query from any question or topic? No query?
So can you briefly explain quick select and how the complexity is different from
Quick select.
yes, sir.
Okay, so there are two things: quick select or fast select. Okay, quick select we are not using MOM algorithm, and fast select we are using MOM algorithm. So okay, let me take this. So how the quick select works actually? So the approach is just use the like some idea of quick sort algorithm. So partition method is same. Not required this. Okay, suppose if you have one random things. Okay, so 4, 1, 3, 6, 8, 5, 4, 2 like this. Okay, suppose you have this 7, 8 elements are there, and the problem is we are getting the either kth smallest or kth largest. Any type of problems we can solve this. So what is the process of this? So for quick select, we pick the element, first element or maybe a last element as a pivot element, so that we are focusing here. Now after getting the pivot element, we applied the partition process. So partition process is just a process in the linear time. We arrange our element in this way. So pivot element will come in the correct position in the sorted order. All the elements which are smaller than this pivot element will come before, and all the elements which are coming as a greater element compared to this pivot will come after that. Okay,
Yes.
so this is the partition actually task. So like suppose if sorted order is there 1, 2, 3, 4, 5, 6, 7, 8. Okay, this is the sorted. So 4 will come at the correct position. The elements which are coming before this will be smaller than this. So this may be in unordered situation, like you will get like ones and 3 and 2 like this. Okay, and all the elements which are coming after this, that will be greater than this. So it's like 7, 8, 6, 5 like this. Okay, so in one steps partition process, you got this type of situation. And after getting this situation, so what means is this? So which actually index it is coming? So this is coming 0, 1, 2, 3, 4, 5, 6, 7. Okay, so because indexing is start from 0, but position is generally considered start from the 1. So if we are getting 3 index for this pivot position, so we can conclude that we have get the like fourth smallest element. Fourth smallest element. So fourth smallest element is this one. Okay, so pivot location is representing the which smallest element this is actually pivot. And now our suppose we are looking for k equal to sixth smallest element, sixth. So first smallest is the smallest one, so like this one, and sixth smallest will be the in the sorted order sixth smallest position this. So after get in the linear type big O n time, we got the position of pivot, and that is also representing the which smallest element is this. And now we can figure out that we are looking for sixth, and we got the position like fourth smallest. So definitely sixth smallest will be come on this half, correct? Only
Yes, sir.
this half. So we can completely discard this part.
Yes.
Okay, now we will apply the same algorithm on the right half. So this now the quick select algorithm we will apply on the right half. Again we will check. So because we got the fourth location, so that means uh, so in the remaining part 7, 8, 6, 2. So we have already got this fourth. Now that means how much location we required? So 6 minus 4, second, for the remaining list, second smallest element we required actually. So that will become overall sixth smallest element. So in this part again we do the same process. Seventh we will select the pivot position, and we will do the process. So 7 will come in between. After that, 6 and 2 like come this, and 8 here. Okay, so means 0, 1, 2, 3. Okay, so we are getting this as a third smallest. Okay, third, but we are looking the second now. So second will come on this part, and we will remove this. Now we have the 6 and 2. Okay, now in this part we will look the second, so only two elements are remaining. So if you will apply the partition process, so this will become 2 6, and this will become a second largest. So in this way we are doing this smallest element. So you can see now the situation is, if our pivot element is coming always in between, then this algorithm will take this recurrence relation Tn equal to, next call will be n by 2 plus partition time big O n. Okay, but if this is the, here the worst case situation is the same of the quick sort. If our pivot is always coming at the corner, then our recurrence relation is become Tn minus 1 plus n. Same. Okay,
Sir, I
then
didn't understand this part. N by 2 plus On, I understood. What
so
how?
worst case situation is just like if you have the sorted order. Okay, like 1 2 3 4 5 6 7
Yes.
8, like, okay, this sorted order is given, and we are looking for the seventh smallest. Okay, so what we'll do, we will pick the pivot element, this one, and this will come at the first position, and then how many elements are remaining. So first step, n step is required, but pivot is coming at the corner. Now remaining elements are n minus 1. Okay, now n minus 1 elements are remaining. We will apply the again same things. We are picking the second as a pivot, so n minus 1 steps are required for this partition process, and this will again come at the corner, so remaining are n minus 2. So here our problem is not dividing into half and half. Okay, problem is not reducing half every time. Here this is
It's just
reducing
one.
one element at a time.
Yeah.
So our task is becoming like this. So n at the first call, say n minus 1, then n minus 2, n minus 3. So this will become like a selection sort or all these steps. So n plus n minus 1 plus n minus 2 plus n minus 3. So this will come a n into n plus 1 divided by 2 n square. Okay, so here every time we are only removing one element from the problem. So because of that, our recurrence relation is like this. So Tn was the initial problem, and next call we have done on n minus 1 element. And the partition was taking big O n time. So this was the recurrence for worst case situation. Okay, because of that, overall complexity for this become a how much? N square. Okay,
Yes, sir.
but if we for fast select, we actually use the MOM, which provide a good pivot that will never come on the corner, that will always come in between approx. So this part actually become a Tn by 2 for fast select and big O n. So then it become a order of n steps. Okay, so for fast select, our complexity become order of n,
Okay,
and
sir.
recurrence relation become this. Because our pivot will always come in between, and we will approx remove half of the part every time instead of one. And same things, if we use the MOM in the quick sort, then we can improve our worst case situation also, which was n square, that we can improve to n log n for quick sort. Okay,
Thank you, sir.
any other query, anyone?
Sir,
Sir,
hello.
Yes.
Sir, this session recorded or not, sir?
This was live streamed.
I'll let it run.
This was live streamed on the YouTube. Sending the link in chat. 1 second. Okay. Okay, any other query, anyone? Okay, then no query. Then we can wind up the session. All the best for quiz 2.
Thank you, sir.
Thank you, sir.